So we're going to revisit this data and look at, first we got to define, anytime you use an x and y variable, you really need to somewhere in it define what x is and what y is. So we're going to say let x be duration of geyser, so this is the old faithful geyser, duration of geyser eruption. And then we're going to let y be the interval until next eruption. All right, and so we can see that this graph that we did of that, where x was how long the geyser erupted, the longer that it erupts, the longer the interval until it erupts again. So if an eruption lasts a really, really long time, that means it'll be a really, really long time until the next eruption happens. If an eruption is very short, then the next eruption will happen sooner than it will be if it was longer. So that's what's going on. Whenever we're writing our equation, we always use y hat as my prediction. All right, and then this graph, although I didn't draw it in there, is something like this. I missed. Let me redraw that. So there, that's a little bit better. So when we're doing this, and let me write down what my R values. My R was 0.9336, which is actually very strong. So when I described this, I said it was a strong positive linear relationship, which means as the amount of time eruption increases, the interval until the next eruption also increases. R is 0.9936, which also shows that it's a strong positive linear relationship. All right. The question then becomes, so is there any other way to know, like, is this a good fit? Now, it looks like it's a good fit, but unfortunately, just like in geometry, there is no it looks like it theorem. You can't say, oh, it looks like it is, so therefore it must be. There are mathematical ways to show whether or not this is a good fit. First thing is this number. The closer this is to 1, the more likely it is that my linear model, my equation, so my equation is what's called a linear model. There's other models you can use, but we're going to be sticking with linear. Is there a way to know, is this a good fit? Well, what we're going to actually look at is if I take, I'm going to turn this way and enlarge this out here a little bit. If we look at every single data point, and we look at how far away they are from the line, that's going to be one thing. And then also, if the line goes right through the middle of the data, about half of the data will be below the line, half of the data is above the line, and they should be relatively sporadic in how they're spread out around the line. So there should be no pattern. So what we're going to do is this distance here, we're going to turn it back to vertical here. So this distance between the line and the data point is what's called a residual. And it's found by taking the y hat value minus the actual y value. All right, and that tells you that distance. All right, so a point that is below the line will have a negative residual because the y hat number is larger. Sorry, it's the other way around. It's y minus y hat. In a point below the line will have a negative residual because its predicted value is larger than the actual value. A data point that is above the line, that one right there, will have a positive residual. And you could find all of these, and so we'll call this R1, we'll call this one here R2, we'll call this one here R3. Each of those is a residual, and then we're going to make another kind of plot called a residual plot, where I will graph x1 and its corresponding residual. I'll graph x2 and its corresponding, oops, made that comma too big, and its corresponding residual. And then I'll plot this point here, x3, and its residual. And I'll do that for every single data point as we go along. All right, so that's what I'm going to do next. So here's how I do it. I'm going to go to my graphing calculator, And after, this is the key, after you find the least squared regression line. So the first thing you have to do is you have to do your graphing calculator and find the least squared regression line. When you do that, your calculator automatically finds the list of residuals. And if you hit on your calculator, second stat, so in yellow it says list, so look at your graphing calculator. There is a list, this is your list of lists. I want you to go into that list of lists and see if you can find the list that, well, we would consider to be my list of residuals. All right, and if you do that, you'll see that that list is called RESID, which stands for residuals. So what I'm going to do then is I'm going to go to here. So then to get to there again is second y equals. What you really should be doing whenever I'm doing any calculator work is have a calculator out that you're also just following along. So I go second y equals, and I get to this. And what I did is I'm selecting a scatter plot again. And this was my X list, so that was my list of eruption duration, so it's eruptions, eruption time. And then this right here, to get that, I did second stat, which is my list of lists, and then I arrow down until I find the resid list, and then I hit enter. Okay. Do not, because it won't work, do not just type in the letters RESID. Your calculator will say, oh, the letters RESID. When you go to second stat, arrow down until you find resid, and then hit enter, your calculator knows that it's actually taking the list of data stored as the list residuals. So we're going to do that, and then, like we always do, we hit zoom 9. And when I do that, this is what my residual plot looks like. And then I hit trace so that you can see that this point right here has that coordinate and that coordinate. And here's what that means, is that when the actual duration, so that was an actual data point, when the duration was 173 minutes, the actual data point that I had, that's right there near my white dot, the actual data point for there was 11 below the line. So this horizontal line represents the y hat line, right, which is why on the last couple slides ago I tilted the graph and said, okay, see if we draw that across horizontal, it's how far it is above and below. So what that means, a negative residual means that my prediction line gave an estimate that was 11 minutes, sorry, this is 173 seconds, 11 minutes. The actual data point was 11 minutes under the prediction. So my actual data point was 11 minutes lower than what I was predicted. Or another way to say it is the line over-predicted the actual time. All right. Over-predicted because the line is over my point. All right. This data point up here is larger than its predicted value, which means that the equation under-predicted how long it actually took. So in this case, this residual will be positive, and because it's above the line, and it means that the actual data point there for that particular x, so the x is right here, that particular y value is higher than the y hat value. And in tracing it, I can see that the residual was 10.51, which means that the actual data point was 10.51 higher than the predicted, and the x in this case, the x right here is 216. So when the eruption lasted 216 seconds, the interval until the next eruption was 10.51 minutes longer than what we expected from the y hat equation. All right, and that's what a residual is. Now, what does a residual do for us? If a residual plot shows no pattern in the points, so all these data points, is there a pattern in those data points? The answer is no, there's no pattern. So that means that the least squared regression line is a good model. Since the residual plot shows no pattern, this means the least squared regression line is a good model for this data. In other words, this data follows a linear pattern. All right? But you need to say this. This is how we interpret this graph. Because I tell people, hey, this is a residual plot. What does the residual plot show? Shows no pattern. So what? Well, then that means that the regression line, or the linear model, is a good model for this data. That is, we've just shown that the linear model, or that this data itself, follows a linear pattern using the least squared regression line of y hat equals 32.33 plus 0.195 x. It means that this equation is a good fit for the data itself. That's what the purpose of a residual plot is. What I want you to do is then go back through what you took for notes, and if you have a data point that is above the least squared regression line, what does that mean in context to this scenario for length of eruption time and interval till the next eruption time, until the next eruption? So if there's a data point that is above the least squared regression line, what does that mean in context to this question? And what is, find a way to work in the word residual correctly into your explanation. So we're probably looking at a sentence or maybe two as you go about this explanation and interpretation. Remember, anytime I say interpretation, I'm also meaning explain this in such a way that if someone doesn't know what the graph is or doesn't know what the data is, that your explanation should make it more clear to those kind of people. All right, that's it, folks. We'll see you in class.